Hi, in this session today, we are going to discuss the machine tool metrology. This is a module 4 of the subject ME 312 Metrology and Instrumentation of Kerala Technological University. I am Radhakrishnan, Department of Mechanical Engineering, Tokach Institute of Technology, Cochin. There are many machine tools at present, and whenever a machine tool is manufactured, it should be tested for various purposes. Three different tests are mainly employed on machine tools. One is a static test, then dynamic test, and practical test. Static test means mainly it is alignment test. That is the alignment accuracy of various parts of the machine. That is called static test. Dynamic test means the test is performed under dynamic loading conditions. That is a dynamic test. That is tested by using the removing the uh, when the machine tool is uh, cutting the metal by removing the chips. Then we can test it. The geometrical checks and practical test. Third one is the practical test. That is that we are manufacturing some demo products from the machine tool for which it is intended. Test processes are must be approximate to the fundamental purpose of for which the machine has been designed. What is the purpose or importance of machine tool testing, that is static testing? Nowadays, the dimension of any workpiece and its surface and geometry depend on the accuracy of machine tool used for its manufacture. Especially in mass production, various components produced should be of high accuracy. The increasing demand for accuracy of the machined components has led to the improvement of geometric accuracy of machine tools. For this purpose, it is very important to carry out various alignment tests on different components of the machine tool. These testings have some advantages. That is it reduces the downtime of the machine. Similarly, it produces high quality machined components. Similarly, reduce power consumption. Similarly, machine reliability and productivity. It reduces machine repair costs. Similarly, installation and repair time will reduce. It reduces machine downtime, increase machine availability. It decreases the wear of bearings, seals, shafts, and couplings. The alignment test also avoids overheating of bearings and couplings. Similarly, reduces vibrations and noise in the machine tools. It significantly reduces the damage to the machine tool components. There are so many advantages by doing this alignment test. So alignment test means we know that a machine tool is a assembled part of many components. For example, lathe, it has various parts like bed, headstock, tailstock, spindle, carriage, saddle, then cross slide, tool post, etc. All these are when it is assembled. As per the Indian standard of these machine tools, it should follow some kind of alignment. That is various factors like straightness and then flatness, parallelism and equidistance and coincidence. Similarly, squareness of straight lines and planes. Similarly, rotation, Rotation, there are many things, are concentricity, eccentricity, out of run out, then axial slip, radial out or a radial through. Similarly, working a movement of all working components. Similarly, spindles, which takes the components to rotate, that its concentricity, axial slip, accuracy of axis and position, etc. That is why this machine tool metrology is very important. That is, various tests are applied before the machine is erected and commissioned. Instruments, simple instruments we are using in machine tool metrology, and that is very common. Instruments are dial gauges, then test mandrels, straight edge, spirit levels, autocollimator, and waviness meter. So in this syllabus, only three equipments, that is machine tools, are considered for the alignment test. One is lathe, second is milling machine, and third one is pillar type drilling machine. So we can see the alignment test on lathe. In lathe, we have the picture shows the idea about the bed. So over the bed, all moving parts are assembled. Hence, it is very important to test the lathe bed for its level. So this is leveling of the machine. So the spirit level which we are using should be 0.04 to 0.06 mm per meter resolution. The spirit level is placed at longitudinally and crosswisely. Longitudinally, why we are looking is, if there is any variation in the level, it will cause for the bending. Transverse type you have to check, otherwise it will be a twist or wind in the bed. So both these we are using the spirit level. In this time, the carriage is kept at the center of the bed and the leveling is checked using the precise spirit level. This level, there is a limit is there for that it should be within that limit, otherwise it will be again it should be reworked. Okay, this is true running of locating cylinder on main spindle. We know that true running means the running of the spindle should be exactly uh, exactly correct, because if there is any offset, then it will rotate in eccentrically. So in order to avoid this eccentricity, similar the components which we are machined using the spindle will be of eccentric shape. Instead of circular shape, it will be an eccentric. Now to avoid that, what we are doing is, the locating cylinder, one cylinder is there, and that cylinder is placed into the chuck or the faceplate. The locating surface should be in a cylindrical shape. Then the dial gauge, you can see that in the picture, the dial gauge is touching, and its plunger, that is the contact point, that is called feeler. The dial gauge is fixed carriage. So we can see that the carriage is there in the lathe. So the dial gauge is fitted using a dial stand. That dial stand is clamped, or sometimes it will be magnetic type. So it will be attached to the carriage, and carriage is brought near the spindle, and the dial gauge from the dial stand and its tip of the dial gauge, that is called feeler, that is made to touch with the cylindrical part of the cylinder, cylindrical shape, that is cylinder, that is locating cylinder. Then the surface is rotated. Slowly it will be rotated. So the value of the dial indicator should not change. There should not be any variation. That means it is perfectly circular. There is no offset or there is no eccentricity. So it should be checked using this arrangement. Next is axial slip of the main spindle with the true running of shoulder face of the spindle nose. We know that headstock, chuck, then axial slip is defined as, say, the axis of the axial spindle movement which follows the same pattern action due to the manufacturer error. Sometimes when it is rotated there will be some changes in the axis offset. To test this axial slip, then the feeler of the dial indicator rests on the face of the locating spindle shoulder. See the second figure, you can see that. Then first it is the dark thick lines. It shows that the thick lines shows that the dial indicator is touching this part, and after that this headstock or this the spindle is rotated 180-degree, and the opposite side also, that is given by the dotted lines, checked. Due to this there should not be any variation. Total error indicated by the gauge we can calculate, but it should be within some kind of certain levels, otherwise it will be rejected. There are three reasons to occur the axial slip. One is due to error in the supporting bearings, then face of the locating shoulder not in the plane perpendicular to the axis of rotation, and irregularities occur at the front face. So due to these three reasons there will be some variations. That variation should not be there. That is the purpose of this test. Next is the true running of headstock center. So you can see that the headstock, then spindle, then the live center, that is a rotating part of headstock. So it should be the running of, true running of is the rotation of headstock about its center or not, to check whether it is about its axe center or not. Headstock center is the live center, we know. When the workpiece is held in the headstock, it should rotate with the headstock center. If not, eccentricity will be generated on the workpiece. The true running of headstock is measured by using the dial indicator. What we are doing is the dial indicator is pressed perpendicular to the taper surface of the live center. Then the variations indicated, then it is slowly rotated, and the variation in the dial indicator that shows the trueness of the headstock center. Next is the parallelism figure. You can see that is 16.5. The same attachment is there. In this, what we are doing is the saddle is in the 16.5, that is the parallelism main spindle to the saddle movement. The same setup is used for movement of upper slide parallel with the main spindle in vertical plane. That is also we can use same thing. Here what we are doing is, the difference is the dial indicator is moved from one end to the other end longitudinally. Then the difference in the reading in the ends, that we are noting it down. That is what is happening in the test of movement of upper slide parallel with the main spindle. Okay. Next, we are going to the parallelism of tailstock guideways with the movement of see this is a tailstock guideways over which a block of the same matching guideways, internal guideways as there for the block. So both will be matching there. Then over that we are placing a dial indicator, and dial indicator moved along this one, along the top surface, similarly on the vertical side. So both will be showing the deviations of the tailstock gateways. Next, parallelism of tailstock sleeve tapper socket to saddle movement. Because tailstock, you know that it is fitted in the right side of the lathe, and it also has a socket, tailstock sleeve tapper socket. Its axis should also be parallel to the saddle. Okay, that is why the same thing what we have done it for the headstock. Similarly, the dial gauge is fitted on a dial indicator stand, and the dial indicator stand is fixed on a carriage or saddle. Then it is the dial indicator is touching or making contact with uh, the tailstock spindle. Then mandrel is put in the sleeve socket, dial gauge is fixed on the tool post, and the plunger is pressed against the mandrel, and the saddle is moved from one side to the other side. Then it is carried in horizontal and vertical planes. Like that we can calculate the parallelism of the tailstock. Alignment of both the centers in vertical plane. Both centers means we know that, and the collars of the lead screw must be exactly square to the screw axis. Otherwise, cyclic endwise movement is set up the same as the natural axial slip of the main spindle. Because it is connected to the main spindle, when it is main spindle is rotated, the lead screw is also rotated when it is connected with the half nut arrangement. So it should be the periodic picture sending for the actual manufacturing site. So this is about this test is very important, and all alignment test should be a very important procedure in the machine tool metrology. Okay, thank you for listening. Thank you.